Hi, and welcome to the next section of Chapter 5, Logarithmic Functions and Their Graphs. We're not actually really going to be looking at graphs. We're going to keep those in mind as we talk about these things, but we are going to look at more of the relationships between exponentials and logarithmics. So we had this last time, and I said it last time, and I'll say it again, is that this graph and everything that's on it is very, very important in making sure that you have a good grasp of these things, about how this is a sort of backwards version of these things. So since they are mirrors of each other, they behave in a very similar fashion, kind of like squares and square roots. We know what the square root of 4 is because we know what 2 squared. We can't do the square root of 4 without thinking about what is 2 squared. Squares and square roots are inverses of each other. Logs and exponentials are inverses of each other. So it is a similar relationship between the two of them. So and that allows us to do particular properties and it lets us figure out like what's going on with these things. Now, one way to translate these two is that if you have an equation, b to the x equals a, that exponent is what the logarithm equals. So this logarithm is this exponent. So b to the x equals a would translate into log base b of a equals x. I'll say that again. B to the x equals a, log base b of a equals x. You want to treat this as another language. This and this are the same way of it's saying the same thing, just in a different way. An example would be if between English and Spanish, my favorite example is the red shoes in English becomes los zapatos rojos in Spanish. There's that translation there. So the article, los, the article in Spanish, stays first. So you got B and B. In English, it goes the adjective and then the noun. Red shoes. So red shoes. But in Spanish, it reverses. You do the noun first and then the adjective. Zapatos is for shoes and then rojos is for red. So A and X change their places. So I would read this if it were like that English phrase. The red shoes becomes los zapatos rojos. The two swap around. So this 8 stays first, but the 3 and the 512 swap places. One way this is also sometimes written is people kind of do this little arrowy thing. This isn't in my brain, but I do want to pitch it to you as well, is it follows this path. That 8 goes to 3 and then 512, because you can translate those things back. That we could say that 8 to the third is 512. 8 to the third is 512. So let's practice some of these. Like we have one side, but we need to translate it into the other side. So we have 3 to the fourth equals 81. If we wanted to translate that into a logarithm, we would use the same base as the exponential. So we would have log, and then its base would be 3, the same base that was in the exponential. Then we grab the other side of the equation. We don't move immediately to the 4. So log base 3 of 81 equals 4. So log base 3 of 81 equals 4, just like 3 to the fourth equals 81. That's the same thing. I just said it in a different language. The language of exponentials and the language of logarithmics. Los zapatos rojos, the red shoes, bouncing back and forth. You need to be bilingual in these things. So if we had this one, we have a base, this is log base 100 of 10,000 equals 2. 10 over here, we would grab the base 100 squared equals 10,000. And that totally makes sense. Like if you square 100, you get 10,000. That's why log of 10,000 equals 2. Because yeah. Treat this as a language. You should be trying to say some of these out loud with me because it makes more sense if you say them out loud. The base of 9 to the 1/2 equals 3. So log base 9 of, we want to go to the other side, 3 equals 1/2. Log base 6 of 1 equals 0. Log base 6 of 1 equals 0. Our base is 6. Our exponent is 0 because logarithms always equal an exponent. This is always an exponent. Look at that. 4, 2, 1/2, 0. 6 to the 0, oh, that's 1. Easy. Base of 5, exponent of -1 equals 0.2. Log base 5 of 0.2 equals -1. Translated. Okay. Lots of examples. Now, there are 2 very special logarithms. You can actually spot them on your calculator. They've got 2 special buttons right there. And you can even use that as a little bit of a cheat because it tells you what the bases are. The little yellow numbers right above them, hopefully you can see it, little yellow numbers right above them tell you what the bases are because they're like, hey, it's just inverses of each other. Like if you go to the square root button and the squared, they're inverses of each other, just like these are inverses of each other. So common log, if you don't write a number there, that is log base 10. So this means the same as log base 10 of something. However, we don't ever write that 10. In fact, if you write that 10, I will mark it wrong. It's inappropriate. It's like writing a square root and you put the 2 in there. Nobody does that and it looks wrong. So don't put the 10 there. Just like you wouldn't put a 2 into a square root. Like you wouldn't write the square root of x like that. That looks wrong. That's not the square root of x. That's the square root of x. That's wrong. So this is good and this is wrong. So an example of this would be if we had log of 100 equaling 2. So that's saying if you translate it back to exponential, that 10 squared equals 100. Ooh. Another important one, a lot of these logarithm things came from exponential problems similar to that E thing that we did last time. And it was with financiers and they needed to know stuff about interest, but then they needed to solve problems with those interest things. So they used E a lot and they used it so often, it felt very natural for them to do, thus natural logarithm. So natural logarithm is log base E. But we never are going to write log base E. We're just going to write ln. So an example of this would be the ln of 2 equals E squared. And this one looks really silly when you translate it. You end up with E to the what? 2 equals E squared. Oh yeah, duh. Okay. Let's write a couple of these ones. So I have e to the x equals 5. If I wanted to translate that into a logarithm, I would write log base e. But as soon as that pops into my head, I'm like, no. I don't write log base e. I write natural log of the other side, 5 equals x. Now, some of these are going to be gross decimals. A lot of these are going to be gross decimals. They're going to be irrational numbers. E is an irrational number. So we got little squiggly equal lines. If you want to write them, I would encourage you to write them, but I'm not going to be super stickler about them. But this is another natural log, so I know it is e, and its exponent is going to be that other side. 832 is approximately 2.3. Got a couple common log ones. It's log base 10, but I don't write the 10. I just write log of the other side, 100,000, equals 5. One more, we're going to translate this one backward. We have log of 1.1 equals -1. Notice I don't say common log, I just say log of 0.1. Common log, you just say log. If you say log and you don't say anything after it, we all assume that it's base 10. So if we translate this to exponential, we get 10 to the -1, because that was the base of our log, equals 0.1. And that makes sense. 10 to the negative 1, that's 0.1. Absolutely. Now, we can do, similar to what I was just doing, we can do sneaky tricks in order to evaluate logarithms exactly without putting them into our calculator. Because I don't have a log base 2 button on my calculator. I do have a log base 10, but I don't have a log base 2. But I could solve a little puzzle by translating. Rather than thinking about this as logarithmic, because my primary language is English. I don't speak Spanish as well. I know a lot of you can speak Spanish better than me. So, but if I translate this Spanish sentence, this logarithm, into English, I'd be able to understand it better. So I think about, okay, well, 2 to the what equals 1/2. Well, all that really happened is it's a fraction. So I just need to bring 2 to the denominator. I can do that with negative exponents. So 2 to the negative 1 equals 1/2. So this equals negative 1. What about this one? This is a common log of 1,000. So this is really asking, if I set it up as an equation, 10 to the what is 1,000? Well, 10 to the third. 10 to the third power is going to be 1,000. So this equals 3. Okay, let's try this one. So this equals something. I would like a new color. I don't know what. I've got 100 to something equals 10. Well, when I'm looking at that one, I'm like, well, the square root of 100 is 10. Well, what's 100 as an exponent? What's the exponent that I can put there? Square root as an exponent, 1/2. Okay, so if I do the square root of 100, that equals 10. So that is like 100 to the 1/2. So this equals, if I would get out of the way, 1/2. So there, I was able to do those logarithms without a calculator. Similar to if I asked you what the square root of 49 is, you don't sit and you don't square root in your head. You think about, what squared is 49? Oh, 7. So that's what the answer is. You want to do the same thing with logarithms. You don't try to logarithm in your head. You think about, okay, there's that base. So that base to what is going to be the thing on the inside? That's how, same deal. Squares and square roots are inverses of each other. Exponentials and logarithms are inverses of each other as well. Thanks. I think I went a little long, but I'll probably cut it down a little bit. So sorry for jumps if there's jumps in here. So thanks for watching. Have a good day.